Hi, good day. I'm Atsushi Sainoki, Associate Professor at Kumamoto University. First of all, I appreciate ISRM Commission on Deep Mining for giving me this opportunity to talk about mining-induced seismicity and its modeling. As you know, mining-induced mining activity at the great depth could cause severe seismic activities in geological structures. So today, particularly, I'm going to talk about challenges in numerical modeling of such seismic activity. So here is a brief my CV. I obtained a bachelor's and a master's degree from Hokkaido University, and then I moved to Canada, and I was enrolled into mining and materials engineering of McGill University. And then I obtained my PhD degree in 2014. Thereafter, I worked as a postdoc at McGill University for 2 years. And then I came back to Japan and became an associate professor at Kumamoto University. Since then, I've been working on research topics about deep hard rock mining, geothermal energy, CCS, mountain tunnel, numerical simulation, heterogeneity, and image analysis. So here is the outlines of today's lecture. So first, I'll talk about the general idea about seismic activity in deep underground mines and the numerical modeling approaches. Okay, and then I will indicate challenges that need to be overcome. After that, I will introduce a new modeling approaches for seismic activity in geological structures in deep underground mines, which is simulation of heterogeneous stress state in a fault damage zone and simulation of seismic activity in a fault zone. Okay. So first, let me talk about the seismic activity in deep underground mine. So these figures show seismic modeling results in deep underground mines. Okay, and then from figure, it is found that the seismic activities are spatially distributed. Okay, and occur not only near mine openings, but also occurs in the regions away from active mining region. For example, in this case, severe seismic activities were observed near this fault. Okay? So these studies suggested that the geological structures exert a large influence on the currents of seismic activity. Okay? So even if the magnitude of stress distribution is small, seismic events can be triggered in geological structures. Okay, so here is another example. So in this case, a large seismic event that caused a strong ground motion predominantly occurred in this shear zone. Yeah. And in this right figure, in this case, a large seismic event occurred in this dike located near this ore. But the distance between this source location and then ore is about the 40 to 50 meter. Okay, so this source location is a bit away. Okay, away from this active mining region. Okay, so as a summary of seismic monitoring results, we can say that the seismic activities in deep underground mines are spatially distributed and occur not only near mine openings, but also away from active mining area. And then there exist seismically active zones located away from openings. And then the geological structures such as stiff dike, shear zones, and fault have a significant influence on the occurrence of seismic events. So to control seismic hazards, like the fault slip burst, it is very important to evaluate and quantify the risk for seismic event with various numerical modeling approaches. Okay, so let me talk about the numerical modeling approaches. Over the decade, significant efforts have been made in modeling induced seismicity. So I summarize important points that need to be considered. Okay, so first we have to model mining activity. Okay, so we need to model ore bodies, and then we need to consider the sequential mining activity. In addition, we need to model the geological structure that could cause seismicity. And then the geological structures can be modeled with the various methods. Okay, so for example, we can use the ubiquitous joint model to simulate shear zone, while the thin fault can be modeled with the interface element. Okay, then we need to think about how we can simulate the failure of rock mass. Okay? So there are many options in terms of the failure criteria and methods to model the nonlinear post-peak behavior, okay? Such as the storing softening or the storing hardening behavior. Okay? And then after that, we need to consider boundary conditions. So we can either constrain displacement on the boundaries, or we apply the stresses on the boundaries. Okay, and then we perform the static or the dynamic analysis. In most of cases, static analysis is performed. Okay, and then this gives you the deformation of the rock mass. So we can calculate the seismic moment, okay, of the event. And then for the dynamic analysis, it allows us to compute seismically radiated energy, okay, in addition to seismic moment. And then and then because the damage of opening is deeply related to the energy radiated from a seismic event, conducting the dynamic analysis is very important. Okay, if we want to estimate the risk with high accuracy. And then as for the numerical modeling method, various methods are available. Okay, like the finite element method, finite difference method, discrete element method, and boundary element method. From these methods, we need to choose the appropriate method, okay, depending on the physical conditions of geological structures to be modeled. Okay. So here is an example of the numerical models, okay, that I constructed. So this left one is a conceptual model representing the deep ad hoc mine with a steeper dipping ore body parallel to this fault, okay, in hanging wall. And then using this model, I conducted the dynamic analysis to simulate the fault slip caused by the extraction of these stopes. Okay. And then in this middle one is a model in the framework of the discrete element method. So in this model, I incorporated the fracture network, okay, to examine the fracture network induced stress concentrations. And then this right one is a mine-wide model that incorporates the several geological structures, okay, like dike and then fault. So this model allows us to examine the stress change in the extensive regions surrounding this ore body. And then the sequential stop extraction was modeled. And then the mining-induced stress change was investigated for this fault and dike. Okay. And then frequently the numerical modeling approaches are combined with the field measurement. Okay. So the waveform obtained from the seismic monitoring systems can be analyzed, okay, to obtain the seismic source parameters, such as the seismic moment, radiated energy, seismic efficiency, slip rate, and so on. And then in terms of the numerical modeling, so first, we have to determine the simulation method, okay? And then, we can construct numerical model. Okay. And then we need to choose appropriate mechanical model that can adequately capture the mechanical behavior of this rock mass. And then after that, we need to input the physical and mechanical parameters to the model. And then after performing the analysis, so seismic source parameters that are the same as those derived from the monitoring system can be obtained, like seismic moment, moment magnitude, and this slip rate, and so on. Okay? And then if there is a large difference between this numerical analysis and field measurement, we need to modify this numerical model, or even we need to change the simulation method. Okay, so this is a kind of the back analysis to calibrate the parameters and numerical modeling method. Okay, and then finally, we can evaluate the risk for future mining activities. And then so in previous studies, so basically these methods have been employed to simulate seismic activities in geological structures. However, in some cases, even after this calibration, the result is not satisfactory. So I will show you some case. Okay. Okay. So challenges. So this is my previous study in 2014. So as can be seen, the many large seismic events took place in this shear zone. And then this right figure shows the corresponding numerical model where we model the shear zone, okay, and this source region, okay, seismic source region. Okay. And then these shear zones are surrounded by the several types of rock mass, such as the metasediment, greenstone, and norite. And then here is overlay, and also this is the backfill region. Okay. And then using the model, so we perform the static analysis, and then we simulate the sequential mining activities. And then based on the results, we computed the fault slip potential. Okay. And then so this figure shows the fault slip potential. And then from this figure, we can find that this fault slip potential is always negative, okay, in spite of the mining activities. And then these negative quantities correspond to the source state below the failure criterion. So this indicates there is no risk for fault slip. So this result is not consistent with the seismic monitoring result, okay, showing the intense seismic activity. Okay, so this is another example. So in this mine, so as I explained, large seismic event took place in this dike located near this property. And then in order to evaluate the potential of seismicity, static analysis was performed using this mine-wide model. And then here is the result of the analysis. So as can be seen that this dike picks up the source state higher than that of the surrounding region because of the high stiffness. And then this result seems quite reasonable. And then these figures shows the source state after extracting the stops in this cavity. So by comparing these two figures, we found that the deviatoric stress increased at this source region, okay, because of the mining activities. However, the comparison of the source state with the more Coulomb failure criterion indicated that this source state is far below the critical value, okay, as can be seen from this figure. So this means also there is no risk of seismic event at this source location. Okay. So as can be seen from these examples, sometimes the conventional numerical modeling method do not yield reasonable stress state at the seismic source region. Okay, so this means that the simulated stress state is far below the critical stress state. Okay, estimated from commonly used failure criteria for the seismic active region in geological structures away from active mining area. So this contradiction will be attributed to the inherent heterogeneity of the physical and mechanical properties of the in-situ rock mass. So this results in the stress concentrations that cannot be simulated with the conventional numerical modeling method. So we need to develop a method to consider the heterogeneous stress state and stress anomalies, okay, that contributed to the occurrence of the seismic event in the region away from active mining area. So these figures illustrate it illustrates the influence of the geological structures. So as can be seen, when there is a specific geological structures such as dike or shear zones, okay, this rock mass becomes very heterogeneous from mechanical and physical point of view. And then this results in a heterogeneous stress state like this. Okay, so what do we need to consider to simulate the stress state? Without a simulation of the heterogeneous stress state, it is difficult to evaluate the risk of induced seismicity that occurs in geological structures. Okay, so this is the purpose of this lecture. Okay, so these two figures shows the source measurement in the field, and then this figure indicates that the rock mass the rock mass stress is significantly affected by the physical and the mechanical characteristics of rock mass, like the degree of fracturing, also the Young's modulus and Poisson's ratio. Okay, so what we need to consider is, so in terms of the macro scale, that we need to consider fault, shear zone, sedimentary basin, folding, interest-below rock, and so on. And then in terms of the mesoscale, we need to consider heterogeneity of Young's modulus and Poisson's ratio. Also, as for the discontinuity, we need to consider heterogeneity of roughness, degree of interlocking, fracture density, length, and orientation. In addition, we may need to consider the degree of weathering and underground water. Okay. So this is an example of the heterogeneous stress state generated by the fracture network. So as can be seen from this left figure, we found that the fracture network in the rock mass significantly affects the in-situ stress state, and then generates the complex stress state in this rock mass. And then this right figure shows that fracture density has a positive correlation with the volume of rock mass with a high brittle shear ratio. So as can be seen, that as fracture density increases, the volume of rock mass with a high brittle shear ratio increases. So it is very important to develop a method to simulate the heterogeneous stress state in geological structures with high accuracy. Okay. So I'm gonna show you my recent work on the simulation of heterogeneous stress state in fault damage zone. Okay. So as shown in this left figure, generally, fault zone is composed of fault core and fault damage zone. Then this fault damage zone is composed of fractured rock mass. Okay? While this fault core accommodates the shear displacement that took place during the evolution of this fault. So I'll show you the method to consider the fracture network in this fault damage zone. Okay. So here is the overall procedure to simulate the complex solid state of a fault damage zone. So first, 3D fracture network is explicitly generated, okay, using the statistical method. Okay? And then next, equivalent continuum model is generated based on the fracture network. Okay? And then finally, the rock mass stress state is simulated using this model. So I'm going to give you a more specific information about each step, okay, for this model construction. So first, in order to generate a discrete fracture network, we have to determine the characteristic of this fault damage zone. Okay, for the purpose, we classify the fractures in the fault damage zone into macro fractures and meso and micro fractures. Okay. And then for the macro fractures, according to previous studies, we assume that the fracture density decreases with the increase in the distance from the fault core, okay, as can be seen from this curve. Okay. In contrast, for meso and micro fractures, we assume that the fracture density is constant, okay, in the fault damage zone. Okay. Then for the macro fracture, we generate a discrete fracture network. Okay. And then its influence on the mechanical behavior of rock mass is taken into account with the crack tensor theory. And then for the meso and the micro fractures, so their influence is implicitly considered with the GSI, okay, which is a geological strength index. Okay. Okay. So here is a three-dimensional discrete fracture network generated. Okay, so this fracture network is composed of more than 4 million fractures. Okay, and then this table lists parameters used to generate this fracture network, and then these are also the equations to generate this fracture. So this one is this equation represents the cumulative distribution function for fracture size, while this one is a probability density function for fracture orientation. Okay, and then this left figure shows the cross section of the fracture network. Okay, so as can be seen, the fracture density varies with the distance from this fault core, and then this right figure is actual fracture density computed from the fracture network. Okay, so as can be seen, near the fault core, the fracture density is very high. Okay, and then it decreases as the distance increases. Then this slide shows the procedure to obtain the equivalent elastic compliance matrix. So as a first step, the Young's modulus of the rock specimen is converted to that of the rock mass with the geological strength index. Okay, so we obtain the elastic compliance matrix of M. Okay, and then by employing the crack tensor theory, we compute the equivalent compliance matrix C. Okay, so C considers the mechanics of the macro fractures. Okay, and then this C is combined with the this C is combined with the compliance matrix, considering the meso and then the microfractures. Okay, and then finally we obtain the matrix T. Okay, and then this T is then input to the zones of this continuum model. Okay, and then so here are the equations to compute the equivalent compliance class tensor according to the cracked tensor theory developed by Oda. Okay. Okay. And then so this table lists the model input parameters. So as explained for the isotropic model, the model input parameters are obtained from the cracked tensor theory, while for the isotropic model, the Young's modulus is 40 gigapascal. Okay, this one is obtained by decreasing the Young's modulus of granite based on the GSI. Okay. And then so this figure shows the boundary conditions. Okay, so as can be seen from this figures, here stresses are applied to the external boundaries. Okay, the vertical stress applied is 10 megapascal, while the horizontal stress applied is 15 megapascal for the x and y directions. Also, that it is to be noted that in the following slide, sigma r denotes the stress applied to the external boundary. Okay, so sigma r means regional stress. Okay, so the minimum one is 10 megapascal, which corresponds to the vertical stress, while the maximum one is 15 megapascal, which corresponding to the horizontal stresses. Yeah. Great. So this is a result. So as can be seen, very complex storage state can be simulated with this method. And then the storage state results from the heterogeneity of the compliance matrix derived from the fractal network and the cracked tensor theory. So as can be seen, near the fault core, the stress is relatively low, okay, because of the high fracture density. While in the damage zone, the stress concentrations takes place due to the heterogeneous stiffness. And then this right figure shows the how stresses are affected by the heterogeneity of the rock mass stiffness caused by the fracture network. As can be seen, the differential stress is increased, okay, compared to the regional stress. Okay, that is a 5 megapascal, while the minimum stress is decreased. So this indicates that the rock mass becomes more failure prone compared to the regional stress state. So it is clear that the seismic activity is prone to occur in the fault damage zone, okay, compared to the post rock. And then to quantify the influence of the parameters used for the generation of fractures, parametric study was conducted. And then this result shows that the stiffness is the most influential factor. Okay. Here, this result. Okay. So figure C shows the influence of the normal and shear stiffnesses, which are the input parameters to compute the equivalent compliance matrix. So this stiffness contribute to the degree of stiffness heterogeneity directory. Similarly, the length is here. The length of fractures is also related to the stiffness, okay? Because it's scale effect. So the length is also affects the component of the equivalent compliance matrix. So that's also it affects the solid state of the damage zone. Okay, and then also with the increase in the degree of stiffness heterogeneity, the stress state becomes more heterogeneous. Okay, and then causing the stress anomalies. Okay. And then finally, I validate the stress distribution in this model in terms of the B value. Okay? For the purpose, the stress of each zone was examined. And then for the zones of which BSR exceeded 0.7, the storing energy stored in the zone was computed. And then seismically radiated energy was estimated with the assumption that the few percentage of storing energy is released as seismic wave when the zone undergoes failure. Finally, assuming a reasonable scale of energy, moment magnitude was evaluated. Okay, so as can be seen in this left figure, seismic events are distributed in this fourth damage zone, and then this right figure shows the B value. Okay, so B value represents the relationship between the event magnitude and its frequency. So large B value means the number of small events are relatively large. So importantly, so it is known that the mining-induced seismicity results in the B value slightly larger than 1.0. So considering the previous studies, so B value estimated from this stress distribution is quite reasonable. Okay. Also, the magnitude of seismic event ranges from -1.0 to 1.5. Sorry. Okay, so basically the magnitude of seismic event detected ranges from -1.0 to 1.5. Okay, so this indicates that the stress anomalies due to the fracture network are related to the occurrence of seismic event with this magnitude range. And then the seismicity with the magnitude larger than 1.5 is most likely related to the other mechanisms, okay, such as asperities in the larger scale. Okay, so here is summary. Okay, so the heterogeneous stress state in the fourth dimension was simulated with equivalent continuum model based on the crack tensor theory, and then the stress anomalies are generated due to the major scale stress heterogeneity resulting from the asperity resulting from the spatially varying stiffness. And then the stress distribution in the fourth dimension seems very reasonable, okay, in terms of the frequency distribution of the moment magnitude. Okay. And then, but in this study, seismic events are not actually simulated, okay, and meaning that the events detected are what was assumed, okay, based on the storing energy. So as a next step, let's examine how the stress heterogeneity in the fourth dimension affects the stress state on the fourth plane, okay, and occurrence of fourth state. Okay, so here is a numerical model constructed in the same way as before. But the difference is that in this model, fourth plane was simulated, okay, like this. So in this model, the red colored zones have an isotropic equivalent complex matrix, okay, calculated with the crack tensor theory. So each zone has a different complex tensor, okay, because of the fracture and because of the heterogeneous fracture network. And then while the gray colored zones are the zone without macro fractures. And at the center of this model, there is fault core, okay, which is modeled with an interface element to simulate fault slip. So here is the numerical simulation procedure. So as a first step, the initial stress condition is simulated, assuming a depth of 2,000 meters with a horizontal to vertical stress ratio of 0.7. Okay, and then note that the to simulate the fault with a deep angle of 70 degrees, the in-situ stress state is rotated. I mean that as can be seen from this figure, the direction of gravity is not vertical. Accordingly, the stresses applied to the model boundary differs between the left and the right boundaries. And this is a bottom boundary condition. Okay? As can be seen at the 4 vertices, the displacement was fixed. Okay, so that's the in order to prevent the rigid movement. Okay, so I'm going to show you the result. So this is the initial stress state simulated with the method. Because as can be seen, that due to the stiffness heterogeneity in the model, a very complex stress state with the stress anomalies was simulated. Yeah. And then after simulating the initial stress state, the effective normal stress in this circular region was decreased in a stepwise manner to initiate photosleep. So the reduction of this confining stress represents the anthropogenic activities, such as a large-scale stops extraction or the fluid injection. Yeah. Also, it is to be noted that the purpose of this study is not to simulate mining activity accurately. Okay, we aim to how the complex stress state on the photodynamic zone affects. We aim to examine how the complex stress state on the photodynamic zone affects the occurrence of seismicity. Okay, so this simple assumption okay, will be okay. Okay, considering the purpose. And then this right flow chart shows shows how to simulate photosleep in dynamic conditions. So after decreasing the effective normal stress by 0.5 megapascal, the stress state on the in the photoplane is examined for each interface element. And then if there is a zone that satisfies the sleep conditions, the analysis condition is changed from static to dynamic. Okay, and then the dynamic analysis is run to simulate photosleep in the dynamic condition. And then the dynamic analysis is stopped, okay, when there is no shear displacement increment on the photoplane. After that, again, the effective normal stress is decreased by 0.5 megapascal in the same way. So this procedure is repeated until the effective normal stress is decreased by 18 megapascal in total. So this figure shows the shear displacement. This figure shows the shear displacement on the photoplane when the effective normal stress is decreased by 5 megapascal. Okay, so we can find that the multiple seismic events were simulated, okay, on this photoplane, and then this is very realistic, okay, and close to the actual field of observations. So this kind of the random distribution of seismic events are affected by the complex and heterogeneous source state of the surrounding damage zone. Okay. Okay. And then so here is results of other stages. So these figures shows the shear displacement on the fault. Okay, as can be seen, the shear displacement increases with the stage, but the shear displacement distribution is not homogeneous. Okay, and then these figures below illustrates each seismic event. Okay, with the different colors. Okay, so as can be seen that in the earlier stages, the area of each seismic event is very small. And then each seismic event is spatially distributed. And then with the increase in stage, the size of the event increases. Okay, but the total number of events decreases. For instance, in 25th stage, the number of events is clearly less compared to the 15 stages. Okay, but the size it was increased. Okay, like this. Okay. Sorry. Okay, and then okay, and then and then okay, in order to quantify the trend of the event size and frequency, a further analysis was conducted. So this left figure, this left figure shows the number of seismic events detected for each stage. So as shown, the number of events increases with the stage, and then it takes the maximum value at 20 stages. Okay, and then decreases. And then this right figure shows the seismic moment, okay, summed at each stage. So comparing the two figures, we found that this trend is similar, okay, between these two figures. But the peak stage is different, okay? So the cumulative seismic moment takes the maximum value in a later stage, okay? Compared to the number of seismic event. So in this case, peak stage is 20, okay? But in terms of the seismic moment, it takes the peak value at 24th stage. So, okay, so this indicates that the reduction of the number of seismic events occurs when large event takes place. Okay. And then this figure also further confirm the assumption. So that this left figure shows the average seismic moment for each stage. So as can be seen at 25th stage, it takes the maximum value. And then this right figure shows the seismic energy, okay, summed for each stage. As can be seen, it takes the maximum value in stages from 23rd to 25th. Okay. And then this histogram shows the distribution of the moment magnitude for seismic event that took place in 15th, 20th, and 25th stage. So as can be seen, the seismic event with the relatively small magnitude take place at 15th stage. Okay, blue. Okay, blue bars. Okay, but at 25th stage, the number of events decreases, but the magnitude increases. Importantly, so this trend implies the decrease in B value, okay, before 25th stage, because of the decrease in the frequency and increase in seismic moment. Okay, so when large seismic event occurs, the frequency of event decreases, but its magnitude increases. Okay. So to verify this postulation, B values were computed for each stage. So as can be seen from these figures, B values decrease with the increase in the stage. So specifically, B value at 15 stage is 1.67, which decreases to 0.76 at 25th stages, okay, where the seismic moment takes the maximum value. So as discussed, B value represents the relative number of strong seismic events with respect to weak ones. So the large B value indicates a relatively large number of small events. So as shown in the previous slide, the numerical model constructed in this study shows that the B value decreases before the occurrence of strong event. And then interestingly, so this trend is similar to the tendency in the field. So as shown in this figure, a B value decreases before the occurrence of strong event. Okay. Before the occurrence of the strong event, main shock in the field. So similar tendencies can be found in other studies. Okay, so these results and then the comparison to the field measurement indicates that this proposed method may be used for the estimation of the risk for the large seismic event, okay, in the field. Okay, so here is a summaries of today's lecture. Okay, so in underground mines, more often than not, the seismic events are spatially distributed and could occur in the region away from mine openings. And then the geological structures are deeply related to the occurrence of the seismic events. Although the various numerical modeling methods are available and the methods can be combined with a field measurement, the simulation of such event is quite challenging. Okay, so the simulated stress state is sometimes far below the failure criteria, indicating the no risk of seismic event. So that there is contradiction. Okay, so to overcome the difficulty, there is a need to simulate the complex heterogeneous stress state in geological structures by considering the various factors. Okay. So in this lecture, the method to consider heterogeneity of the rock mass stiffness within the fracture network was introduced to simulate the major scale stress heterogeneity in the 4 dimension. Especially also the spatially distributed seismic events were then simulated, okay? Which conventional method could not reproduce. And then the frequency distribution of the magnitude varies with the effective stress change, okay, which is qualitatively consistent with the field measurement. Okay. So the proposed method could contribute to improving the accuracy of induced seismicity simulation and estimating the risk for the large seismic event. Okay, thank you so much.